Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Class 11th Physics Laws of Motion Chapter 5 NCERT Solution Part 3. Our mission is to provide free classes on YouTube for all students of class 6 to class 12, special classes for the student preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we begin our today's lesson, we request you to subscribe, like, and share our channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's lesson. In the last session, we have discussed till question number 5.20. Today we'll start from question number 5.21. A stone of mass 0.25 kg tied to the end of the string is whirled round in a circle of radius 1.5 meter wide, a speed of 40 revolutions per minute in a horizontal plane. What is the tension in the string? What is the maximum speed with which the stone can be whirled around if the string can withstand a maximum tension of 200 Newton? Question number 5.21 solution. So mass of the stone m is equal to 0.25 kg. Radius of the circle r is equal to 1.5 meter. Number of revolution per second n is equal to 40 upon 60, that is 2 upon 3 rotation per minute per second. Angular velocity omega is equal to v upon r, that is 2 pi n. Equation number 1. The centripetal force for the stone is provided by the tension T in the string, that is T is equal to F centripetal force, that means centripetal force, which is equal to mv square upon r, which is equal to mr omega square. And we can write, instead of omega, we can write 2 pi n. So mr 2 pi n square. So here we putting the value of m, r, n, pi, etc. We get 0.25 into 10 into 1.5 into 2 into 3.14 into 2 by 3 whole square. So upon solving we get 6.57 Newton. Maximum tension in the string T max is equal to 200 Newton. T max is equal to mv square, mv max square upon r. Therefore, V max is equal to T max into R upon M, that is 200 into 1.5 upon 0.25, which is equal to under root 1200, which is equal to 34.64 meter per second. Therefore, total max speed of the stone is 34.64 meter per second. And this is the answer. Let us move to the next question. Now we'll do 5.22. If in exercise 5.21 the speed of the stone is increased beyond the maximum per permissible value and the string breaks suddenly, which of the following correctly describe the trajectory of the stone after string breaks? A. The stone moves radially outwards. B. The stone flights off tangentially from the instant of the string breaks. C. The stone flies off at an angle with the tangent whose magnitude depends on the speed of the particle. So, option B is correct. The explanation is what when the string breaks, the stone will move in the direction of the velocity at that instant. According to the first law of motion, the direction of the velocity is tangential to the path of the stone at that instant. Hence, the stone will fly off tangentially from the instant of the string broke. So, if this is the thing, then at this instant, if the stone breaks, then it will make a tangent. This is the string holding the stone and it will move in this direction. Now let us see the next question. Now let us solve question 5.23. Explain why a horse cannot pull a cart and run in empty space. B. Passengers are thrown forward from their seat when a speeding bus stops suddenly. C. It is easier to pull a lawn mower than to push it. D. A cricketer moves his hand backward while holding a catch. So let us solve the first one. Let us see the answer for the first one. A horse cannot pull a cart and run in empty space. So, in order to pull a cart, a horse pushes the ground backward with same force. The ground, in turn, exerts a equal and opposite reaction force upon the feet of the horse. The reaction force causes the horse to move forward. An empty space is devoid of any such reaction. Therefore, a horse cannot pull a cart and run in empty space. So, let us see the next part of the question. Next question is 5.23 B. Passengers are thrown forward when their seats from their seats when a speeding bus stops suddenly. So, when a speeding bus stops suddenly, the lower portion of passenger's body, which is in contact with the seat, suddenly comes to rest. However, the upper portion tends to remaining in the motion as per the first law of motion. As a result, the passenger's upper part of the body is thrown forward in the direction in which bus was moving. Let us see the next question. Now we'll solve the C part. It is easier to pull a lawn mower than push it than to push it. So while pulling a lawn mower, a force at an angle theta is applied on it. So we can see in this figure. This is the weight mg and this is the force F. So if and this is the angle theta with the horizontal. So the horizontal component of this force F is equal to F cos theta and vertical component of this force F is equal to F sin theta. So the vertical component of this applied force acts upward. This reduces the effective weight of the mower. On the other hand, while pushing the lawn mower, a force at an angle theta is applied on it as shown in the following figure. So in this case also the weight is acting downward mg, and the pulling force, that is F, is acting with an angle theta with the horizontal. So mm, uh, we can draw the vertical and horizontal components as F sine theta here, and this will be F sine theta again. This side will be F cos theta, and upward will be F cos theta. Now in this case, the vertical component of the applied force acts in the direction of the weight of the mover. This increases the effect of the weight of the mover. So vertical component F sine theta and mg are in the same direction, so it increases the weight of the mover. Since the effective weight of the lone mower is lesser in the first case, pulling the lone mower is easier than pushing it. But in this case, what happens? It is more effective. Mg and F cos theta both are acting downward, so this two forces are acting here, so it is difficult to push it. Now we'll see the last part, that is D. A cricketer moves his hand backward while holding a catch. According to Newton's second law of motion, we have an equation of motion, that is F is equal to ma, that is m delta v upon delta t. This is equation 1, where F stopping force experienced by the cricketer the ball as he catches the ball. M is the mass of the ball, delta t time of impact of the ball with the hand. So it can be inferred with equation 1 that the impact force is inversely proportional to the impact time. That is, F is inversely proportional to 1 by delta t. This is equation 2. Equation 2 shows that the force experienced by the cricketer decrease if the time of impact increase, and vice versa. While taking a catch, a cricketer moves his hand backward so as to increase the time impact, that is delta t. This in turn results in the decrease in stopping force, thereby preventing the hands of the cricketer for getting hurt. So 5.24. Figure 5.17 shows the position time graph of a body of mass zero point zero 0.04 kg. Suggests a suitable physical context for this motion. What is the time between two consecutive impulse difference by the body? What is the magnitude of each impulse? So a ball rebound between the two walls located at x is equal to 0 and x is equal to 2 centimeter. After every 2 seconds, the ball receives an impulse of magnitude 0.08 into 10 to the minus 2 kg meter per second from the walls. The given graph shows that a body changes its direction of motion every 2 seconds. Physically, this situation can be visualized as the ball rebouncing to and fro between two stationary walls situated between the position x is equal to 0 and x is equal to 2 centimeter. Since the slope of xt graph reverse every reverse after every 2 seconds, the ball collides with the ball after every 2 seconds. Therefore, ball receives an impulse after every 2 seconds. Mass of the ball m is equal to 0.04 The slope of the graph gives the velocity of the ball. Using the graph, we can calculate initial velocity u as u is equal to 2 minus 0 into 10 to the minus 2 upon 2 minus 0, that is 10 to the minus 2 meter per second. Velocity of the ball before collision u is equal to 10 to the power minus 2 meter per second. Velocity of the ball after collision v is equal to minus 10 to the power minus 2 meter per second. Here negative sign arise as the ball reverses its direction of motion. So magnitude of impulse is equal to change in momentum, that is mv minus mu, that is put the value of m and take m as a common, that is 0.04 v minus u. 0.04 minus 10 to the power minus 2 minus 10 to the power minus 2, which is equal to zero point 0.8 into 10 to the power minus 2 kg meter per second. So this is the answer. Let us move to the next question. The next question is 5.25. So figure 5.18 shows a man standing stationary with respect to the horizontal conveyor belt that is accelerating with 1 meter per second square. When is the net force on the man? What is the net force on the man? If the coefficient of the static friction between the man's shoes and the belt is zero point 0.2, up to what acceleration if the belt can the man continues with to be stationary relative to the belt. Mass of the man is equal to 65 kg. So solution of 5.25 is mass of the man is 65 kg. Acceleration of the belt is A is equal to 1 meter per second square. Coefficient of static friction, that is mu, is equal to zero point 0.2. The net force F acting on the man is given by Newton's second law of motion as F net is equal to ma is equal to 65 into 1, that is 65 Newton. The man will continue to be stationary with respect to the conveying belt until net force on the man is less than than or equal to the frictional force Fi entered by the belt. The man will continue to be stationary with respect to the conveyor belt until the net force of the man is less than the equal to the frictional force Fi exerted by the belt, that is F net is equal to Fx, that is F net we can write m a dash, and Fx we can write mu mg. A dash is equal to zero point 0.2 into 10, which is equal to 2 meter per second. Therefore, the maximum acceleration of the belt up to which the man need man can stand stationary is 2 meter per second square. So the next question is 5.26. A stone of mass m tied to the end of the string revolves in a vertical circle of radius r. The net force at the lowest and highest point of the circle directed vertically downwards r. Choose the correct alternative. Lowest point mg minus T1, highest point mg plus T2. Again, B mg plus T1, mg minus T2. C mg plus T1 minus mp1 square upon R, mg minus T2 plus mp1 square upon R, mg minus T1 minus mp1 square upon R. T1 and V1 denotes the tension and speed of the at the lowest point. T2 and V2 denotes the corresponding value at the highest point. Now let us see the solution. So solution of 5.26 is the free body diagram of the stone at the lowest point is shown in the figure. So at the lowest point, the tension T is acting upward, weight is acting downward. According to Newton's second law of motion, the net force acting on the same at this position is equal to the centripetal force. That is, F net is equal to T minus mg, which is equal to mp1 square upon r, which is equation number 1, where v1 is the velocity of the lowest point. The free body diagram of the stone is shown at the highest point, is shown as follow. So here tension T and mg both are acting downward. Using Newton's second law of motion, we have T plus mg is equal to mv2 square upon r. This is equation 2, where v2 is equal to velocity of the at the highest point. In it is clear from the equation, that equation 1 and 2, that the net force acting at using Newton's second law of motion, we have T plus mg is equal to mv2 square upon r, that is equation number 2, where v2 is equal to velocity at the highest point. In this case, from equation 1 and 2, that the net force acting at the lowest and highest point are respectively T minus mg and T plus mg. Now we'll do question number 5.27. A helicopter of mass 1000 kg rise with a vertical acceleration of 15 meter per second square. The crew and the passenger weigh 300 kg. Give the magnitude and direction of A, force on the floor by the crew and passenger. B, acting on the floor on the rotor of helicopter, so the surrounding air. C, force on the helicopter due to the surrounding air. So we'll answer this question one by one. So 5.27, mass of the helicopter m mh is equal to 1000 kg. Mass of the crew and passenger mb is equal to 300. Total mass of the system m is equal to 1300 kg. Acceleration of the helicopter A is equal to 15 meter per second square. A. With the Newton's second law of motion, the reaction force mr1 f fr1 on the system by the floor can be calculated as r minus mpg is equal to ma. Then mp bracket g plus a, put the value of mp, that is 300, bracket 10 plus 15 is equal to 300 into 25, that is 7500 Newton. Since the helicopter is accelerating vertically upward, the reaction force will be dec- will be directed upward. Follow as per the Newton's third law of motion. The force on the floor by the crew and passenger is 7500 Newton. Directly, so by using second law of motion, the reaction force R dash experienced by the helicopter can be calculated as R dash minus mg is equal to ma. So is equal to mg plus a. 1300 is 10 plus 15. So the answer is 1300 into 20. So 32500 Newton. So now we'll do question 2 5.28. A stream of water flows horizontally with a velocity of 15 meter per second. Gases out. So let us see the problem again. A stream of water following horizontally with a speed of 15 meter per second. Gas out of the of a tube of cross-sectional area 10 to the power minus 2 meters square and hits the vertical wall nearby. What is the force exerted on the wall by the impact of water, assuming it has not reformed, not rebound? So B is equal to reaction force experienced by the helicopter from the surrounding air is acting upward. Here, as many Newton's third law of motion, the action of the rotor on sur- on surrounding area air with will be 32500 Newton, directly directed towards downward. So let us do 5.29. 10 1 rupee note coin, 1 rupee coin are pushed on the top of each other on the video. Each coin has so 10 1 rupee coin but are put on the top of each other on a table. Each coin has a mass m. Give the magnitude and direction of first. A. The force on the seventh coin counted with the from the bottom. Due to all the coins are not its top, the force on the seventh coin. B. The force on the seventh coin by the 18th coin. C. The reaction of sixth coin on the seventh coin. So 10 rupee, 10 1 rupee coin are put on the top of each of the table. Each coin has a magnitude m. Give the magnitude and direction of a. The on the seventh force on the seventh coin counted from the bottom due to all the coins on its top. B. The acceleration. The force. So what we are doing? We are doing 5.29. B. The force on the seventh coin by the eighth coin, and C is the reaction of the sixth coin on the seventh coin. So the next problem is 5.25. A force on the seventh coin is extracted by the weight of the coin on that surface. Weight of nuclei. The weight of one coin is equal to mg. The weight of three coin is equal to 3 mg. Hence, the force extracted on the seventh coin by the third coins on its health on its top of 3 gram. This force act vertically downward. Force on the seventh coin by the eighth coin is because of the weight of the eighth coin and the other two coin, ninth and 10th on its top. While weight of the eighth coin is equal to mg. Similarly, weight of the ninth coin is equal to mg and weight of the 10th coin is equal to mg. The total weight of these three coins is equal to 3 mg. Hence, the force created, the force extracted on the seventh coin by the eighth coin is 3 mg. This forecast vertically shows the common things which we can carry out for the vertically downward motion. So the sixth coin experiences a downward force because of the weight of four coins 5, 6, 7, 8, 9, 10, 7th, 8th, 9th, and 10th on its top. Therefore, the total downward force experienced by the sixth coin is 4 mg. As per Newton's third law of motion, the sixth coin will an angle, produce an equal reaction more on seventh coin, but in opposite direction. Hence, the reaction force of sixth coin on the seventh coin is of magnitude 4 pi. This force acts in the upward direction. So let us see the next question. Now we'll do question number. Now we'll do question 30, 5.30. An aircraft executes a horizontal loop at at a speed of 720 km per hour with a wings banked at 15 degree. What what is the radius of the loop? So let us see the solution. So speed of the aircraft v is equal to 720 km per hour. Convert it into meter per second, which is 200 meter per second. Acceleration due to gravity g is equal to 10 meter per second square. Angle of banking theta is equal to 15. For audience u, for radius r of the loop, we have the relation tan theta is equal to v square upon rg. R is equal to v square upon g tan theta. So r is equal to v square upon g tan theta. So putting the values in numerator and denominator, we get 200 into 200 upon 10 into 10, 15 degree. On solving, we get 14925.37 meter, and we can write it as 14.92 kilometer. And this is the end of today's lesson. Before we close, we request you to subscribe, like, and share our channel. Please click on the subscribe button to support us. So please subscribe, like, and share our channel among your friends, relatives, and other people. Please click on the subscribe button to support us, and also click on the subscribe bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for your help and watching these videos.